Okay, in this video, we're going to look at using sigma notation to write and evaluate sums, approximate areas using left-Riemann sums, right-Riemann sums, midpoint, and trapezoidal method. And then we're going to find the area in the region in a plane using limits and summation. So to start with, we need to figure out what summation notation is and what is a summation. So the summation from I equals 1 to n of a sub I is equal to, and now summation means I take a sub 1 plus a sub 2 plus a sub 3, and I keep adding up integers all the way until I get to that top value of a sub n. In this notation, some important things identified as I is called the index of summation. The starting at 1 is called our lower bound, and where we end is a sub n is called the upper bound. And this fancy looking E is called the summation notation or the summation symbol. Okay, so in words, this would be where I is the index of summation, and a sub I is our function, our operation, and it is the ith term in the sum, and the upper and lower bounds of the summation in this example is n is the upper bound, and 1 is the lower bound. The lower bound must be constants, and the upper bound must be constant with respect to the index of summation. However, the lower bound does not have to start with 1. Okay. Any integer less than or equal to the upper bound is legitimate lower bound value. All right, so let's do some summation. So here I'm going to do the summation from I equals 1 to 6 of I to the 4th. Okay, so what this notation means is I replace I with 1, so it becomes 1 to the 4th, plus now I increase by an integer until I get to 6. So 2 to the 4th, 3 to the 4th, 4 to the 4th, 5 to the 4th, plus 6 to the 4th. And then I just evaluate each of these and add those values together. And so the summation of I equals 1 to 6 of I to the 4th is 2,275. Okay, you try the next one. Now notice it doesn't have to be the I variable. We can use any variable we want. In this case, we use k. So summation of k equals 0 to 5 of k plus 1 would be 0 plus 1, plus 1 plus 1, plus 2 plus 1, plus 3 plus 1, plus 4 plus 1, plus 5 plus 1. You do not have to write this step here. You can go straight to this next step as 1 plus 2 plus 3 plus 4 plus 5 plus 6. Adding those together, we get the summation is equal to 21. Now, when the small and our lower bound and upper bound are relatively close together, it's pretty easy to do. But for large n values, we need to do some summation formulas. So the summation of I equals 1 to n of some number, a constant, is just the constant times n. And the summation of I equals 1 to n of I squared is equal to the upper bound, which is n, times n plus 1 times n, 2n plus 2 all over 6. And the summation of I equals 1 to n of I is equal to n times n plus 1 divided by 2. And the summation of I equals 1 to n of I cubed is equal to n squared times n plus 1, quantity squared, divided by 4. You need to memorize these 4 summation formulas. And so we only have to memorize these 4 because any other summation can be rewritten in terms of one of these 4. So if I had the summation of I to the 4th, I could rewrite that as I squared quantity squared, and I could substitute my I squared formula in, evaluate that, and just square my answer. So that's the reason why we only have to memorize these 4. Okay, we're going to use the properties of summation to rewrite this expression using summation notation, and then we're going to evaluate for n equals 10, relatively small value, then 100, then 10,000. You'll see how handy it is once we get to these large values. So to do this, one property of summation is we can distribute the summation notation to each term. So I can rewrite this as summation of k equals 1 to n of 3k squared plus summation of k equals 1 to n of 7k minus the summation of k equals 1 to n of 10. Another cool factor of summation is constants can factor out. So I can rewrite this first term as 3 times the summation of k equals 1 to n of k squared plus 7 times the summation of k equals 1 to k to n of k, and minus the summation of k equals 1 to n of 10. Now for k squared, summation of k equals 1 to n of k squared, I'm going to use that I squared formula, and so I'm going to replace that with that formula we found earlier, which is n times n plus 1 divided by 2. So here I substituted in our formulas that we just learned, And now I'm going to simplify a little bit. So 3 over 6 simplifies down to just 1 over 2. So I can simplify that. And then here I'm going to distribute that 7 into the terms. And we have a common denominator, so I can rewrite one fraction. I'm going to start multiplying some of these together. So for example, 7n times n plus 1 will be 7n squared plus 7n. And now I'm going to multiply all together and combine like terms to simplify our expression. So we end up the summation is equal to n cubed plus 5n squared minus 6n. And so now I'm ready to evaluate the summation when my upper bound is 10, and when my upper bound is 100, and my upper bound is 1,000. So to do that, let me write it up here. I simply replace every n with 10 and evaluate that, and I end up with 1,440. Next, I just go to our formula here and replace n with 100. And I get 1,049,400. And then replacing n with 10,000. We get 1,000,494,400,000. Okay, now I want you to try this next example. Find the summation of k equals 1 of n of 5k squared times k plus 4. Okay, to work this problem, you're going to start by distributing the 5k squared to each term, so we can get rid of our parentheses because we need to get rid of the multiplication operation. And then I can distribute the summation symbol to each term and factor the constant out of each summation term. And then replace k squared and k cubed with our summation formulas that we learned earlier. And now it's just simplifying this expression down. And I do want you to simplify it down. Now that we found our summation formula for n, we're going to now evaluate the summation for n equals 100. So do that next. Sorry, n equals 10. Evaluate this for n equals 10. Simply replace every n with 10 and simplify down or evaluate the value. And we get that the summation is equal to 22,825. Now for n equals 100. We get n is 134,294,500. 279,500. And then for n is equal to 10,000. Is 12, 509, 167, 790, 0,00000. Okay, one application of summations is to find the area of a plane region. We're going to use this to approximate area first, and then we're going to find the exact area. So to approximate the area, we're going to learn 4 techniques. First technique is called the left-Riemann sum, which is abbreviated L sub n, right-Riemann sum, R sub n, midpoint Riemann sum, M of n, and trapezoidal method, T of n, where n is the number of rectangles that we're going to form in order to evaluate this. So I'll give you an example. If I wanted to find the left-Riemann sum of the area under this curve. Okay, let's say I want to find the area under this curve from A to B. And I'm going to use left-Riemann sum to approximate this. Let me move the A in a little bit so we don't get mixed up with the axes when I'm writing this. If I wanted to find left-Riemann sum, let's say I divide this section into 3 equal subintervals to approximate the area under the curve. Okay, so what left-Riemann sum of 3 means, I take the number line from A to B and divide it into 3 equally spaced intervals. And then I draw a line from the left endpoint of the first interval and go across and make a rectangle. And then from the next interval and for our last interval, and notice the height of those rectangles determined by the function value at the left endpoint of the interval. And so to approximate the area, I'm going to find the area of each of these rectangles, and I'm going to add them together. So the summation of the areas of the rectangles is what left-Riemann sum is. When the height of the rectangle is drawn from the left endpoint of your interval, subinterval, to the function value. And so if our purple graph is f of x, then the height of that first rectangle, this rectangle here, can be found by taking f evaluated at a times the width of the rectangle. And the width of the rectangle is our change in our x value. So we're going to call that delta x. And that gives us the area of this. Now to find the area of the next rectangle, I'm going to take the height of that function value, and this time is the height at, we're going to call this endpoint a sub 1. So it's going to be the function value evaluated at a sub 1. That'll be the height times width, which is delta x, plus for our third rectangle to find its area, this area here, we will take the height of that function, which is the function value evaluated at a sub 2, times our width, which is delta x. That's the left-Riemann sum. Now we usually write it, notice that all three of these terms have delta x in common, so we usually factor out and write delta x times f of a plus f of a1 plus f of a2. Okay, I'm going to use left-Riemann sum to evaluate the integral, the area under the curve, right-Riemann sum to evaluate the area under the curve here. And so this time we're going from the right endpoint of each, the height of the function is determined by the right endpoint of each interval. So you notice our area is going to be completely different this time. But our process is the same. I want to find the area of the first rectangle to find its area under the curve. And so that would be the height of that rectangle is determined by f at a sub 1 times by our width of the rectangle, which is delta x, plus f of a sub 2 for the height of this new rectangle, times by delta x, the width of the rectangle, plus the height of this last rectangle, which is f at x a sub 3, times by the width of delta x. Again, I can factor out that delta x and write this as delta x times f of a sub 1 plus f of a sub 2 plus f of a sub 3 as my right Riemann sum. Now let's talk about the midpoint Riemann sum. You can probably figure out that what this is going to mean is we're going to find the height of each individual rectangle in our subdivisions by the midpoint of that subdivision. All right, so our midpoint Riemann sum with subintervals of 3, so M3, figure out the height of this function at that midpoint. And then we want to draw a rectangle from there. And then each of these rectangles will be drawn from the height, the function value's height at the midpoint of each subinterval. All right, so how would we figure out the area of the first rectangle? So the area of the first rectangle is still height times width. Okay. I'm going to call this midpoint value here C1, and then M1 and M2 and M3. So we're going to find the function value evaluated at M1 times by the width of delta x, plus the function value for the next rectangle, the next area of the rectangle, is a function value at M2 times delta x, which is this area. And then to find the last rectangle's area, I would take f of M3 times delta x. And again, I can factor out that delta x and rewrite this as just delta x times f of M1 plus f of M2 plus f of M3. That is how you find the midpoint approximation of area under a curve. Okay, last but not least, we're going to talk about the trapezoidal method of finding the midpoint finding the area under a curve. Now, for the trapezoidal method, we need to refer back to the area of a trapezoid. So recall that to find the area of a trapezoid, you have a trapezoid has two parallel bases and two sides that are not necessarily parallel. So the two parallel bases I'll call base 1, base 2, and the perpendicular distance between those two parallel bases we call the height. And so the area formula for a trapezoid is the sum of your two bases, so b1 plus b2, divided by 2 times the height. Okay, in our drawing, I'm going to do this first subinterval from a to a1. I'm going to draw a trapezoid, so that I'm going to do my heights as the height of the function value at those two endpoints. Those are my two bases. And then just connect it with a straight line. So this is base 1, this is base 2. All right, and so our height, or our perpendicular distance there, is still delta x. So to find trapezoidal T3, trapezoidal method with three subintervals for this diagram. So T3 is equal to the summation of the two bases. So for the area of this trapezoid, we're going to find base 1 plus base 2. So that would be f of a at 0 plus f of a at 1 to get this other parallel height, or base, divided by 2 times our height, and our height is considered delta x. In this case, of the width. Okay, now I'm going to do the same thing for our next rectangle, for our next subinterval, and that's going to be this trapezoid. To find the area of this pink trapezoid, I would take our function evaluated of a sub 1 plus our function evaluated of a sub 2 divided by 2 all times by delta x. And then for our last trapezoid, which is this, so this last trapezoid, we're going to take our function value at a of 2 plus our function value of a of 3 divided by 2 and times it by delta x. Now notice all of these have delta x and dividing by 2 in common, so I can factor out my delta x over 2. And then that leaves us with f of a sub 1, a sub 0 plus f of a sub 1 plus f of a sub 1 plus f of a sub 2 plus f of a sub 2 plus f of a sub 3. Now notice that I have some repeats. So we usually write a trapezoid method as delta x over 2 times f of the left endpoint, which is a naught, plus 2 times all the endpoints, the interior endpoints of trapezoids, plus, and then the last b, the last endpoint, we only use once. So the first and last are once, and all the ones in between are doubled. And that is the trapezoidal formula to find the approximation using the trapezoidal method to approximate the area under a curve. Now let's try a few examples. So in part A here, I have the line y equals 1/2 x plus 5. On the interval from 0 to 8, I want to find the area, I want to approximate the area under the curve with 4 subintervals using the left-Riemann sum. So first thing I have to do is figure out what delta x is. Now the formula to find our change in delta x is really easy. We take our right endpoint minus our left endpoint, divide by a number of subintervals that we want, or number of rectangles we want to form. So that's b minus a over n. So for AI, my first example here, that's what I want to do. I want to find my delta x first. So delta x would be equal to 8 minus 0 divided by 4, or because we want 4 subintervals, and so therefore delta x is equal to 2. So I'm going to count by 2, starting at x equals 0 and ending at x equals 8, to approximate the area in the curve from 0 to 8. Now I'm going to draw left-Riemann sum, so I'm drawing rectangles with a height starting at the left endpoint of each of those subintervals, and I'm doing 4 rectangles. And now our L4, our left-Riemann sum with 4 subintervals, will be fine by we can find that by taking the area of each of these rectangles. Now notice that again delta x is in common, and so we can just factor out the delta x instead of writing it every time. So if we want to find the area under the curve here, that would be delta x, which is 2, times by our function value at the left endpoint, which is f of 0, plus our function value for the next rectangle. We need the height and the area of our next rectangle we find by taking 2 times our function value at f of 2. And for a third rectangle, we take our delta x, which is 2, times it by our function value at our left endpoint of 4. And for the last rectangle, we take our delta x, which is 2, times it by our function value at our left endpoint of f of 6. Notice all these have 2 in common, so I could factor out my GCF, and you could have also written this first step as 2 times f of 0 plus f of 2 plus f of 4 plus f of 6. And that's how I normally write it, but you can do either one of these. So L4 would be 2 times, well, let's evaluate each of these. I can do two ways. I can replace every x with 0 in my equation I gave you to get 5, or I could look at the graph and see that f of 2 has a height of 4, f of 4 has a height of 3, and f of 6 has a height of 2. 5 plus 4 plus 3 plus 2 gives us 14, times 2 gives us 28. So area under that curve is 28. I want you to try the next example, same function, but this time find the right Riemann sum of 4 subintervals. So in this case, since we're still doing the same interval from 0 to 8 in 4 subintervals, our delta x is the same, which is 2. But this time each rectangle is going to be constructed with the height determined by the right endpoint, so that's going to be f of 2. For the second rectangle, my height is determined by f of 4. My third rectangle, my height is determined by the function value at 6. And the last rectangle, my height is determined by my function value at 8. Okay, now substitution time. So R4 is equal to 2 times. And we know that delta function value at 2 for that first rectangle has a height of 4, plus at f of 4 is equal to 3, f of 6 is equal to 2, and f of 8 is equal to 1. 4 plus 3 plus 2 plus 1, all times by 2, gives us an area, approximate area of 20. So notice that these are very different. Approximations will be different based on how you did it. The purple graph, the first one we did, is an overestimation of our area, and the second one is an underestimation. The midpoint method and the trapezoidal method will give us a closer approximation. So this time I want to change equation. I'm going to figure out the midpoint summation of this quadratic from -1 to 2 with 3 subintervals. Try it out. We need to start by finding our delta x. So our delta x is equal to b minus a, so that's 2 minus a -1, or 2 plus 1, divided by n in this case, so 3 subintervals, so n is 3. So that gives us 3 divided by 3, which is 1. So our delta x is 1. For our first subinterval, we're going to do the midpoint here, and then evaluate our function value. Second rectangle is drawn from the midpoint of the second subinterval, and third rectangle is drawn from the midpoint of the third subinterval. Now, it's very, very important that you notice that how I draw this, I purposely drew these a little bit off because you cannot go by your diagram when you figure out your function value at M1, M2, and M3 because your drawing might not be perfect. So I do need to find the function value, and our M1 would be at -1/2. Our midpoint of our second interval would be at 1/2, and the midpoint of the third interval would be at 3/2. To find that function value, I'm actually going to plug in -1/2 into our original function that was given to us. And simplify that down, I end up with 39/4. When I substitute 1/2 in, I get 31/4. And when I substitute 3/2 in, I get 15/4, which is definitely not what I have drawn. Adding those together and timesing by 1, I end up with the area approximation under this curve from -1 to 2 is approximately 85/4 when I use the midpoint formula. Okay, I want you to try the trapezoidal method here. Same equation, same interval, but this time we're going to approximate using the trapezoidal method with n equal to 3. Okay, so our delta x is the same as what we did before, so delta x is still 1. And then we can factor out the delta x and dividing by 2. So here's what the sketch of this area would look like. All right, so find the area of the first trapezoid. I'll take delta x times b1 times plus b2 divided by 2. So I'm going to factor out the delta x and divide by 2, and just take my f of left endpoint, 2 times my middle endpoint, 2 times the next middle endpoint, which would be f of 1, plus f at 2. That's my a and b I only see once. All the other endpoints I double on the interior. Then I'm going to plug that into my calculator, plug that into the function, evaluate the function at -1. And I get 10. At 0, I get 9. At 1, I get 6. And at 2, I get 1. Adding those together, I end up with an answer of the approximate area is 41/2. Okay, I know this says your turn, but I'm going to do the first one. I'm going to use this table of value to approximate the left-Riemann sum using 3 equal subintervals. So left 3, L3. I need to fill out my delta x. So delta x would be 6 minus 0 divided by 3, which gives us delta x is equal to 2. So I have one rectangle from 0 to 2. another rectangle drawn from 2 to 4, and my third rectangle is from 4 to 6. So I kind of draw that on there so I can know where my rectangles are. So if I'm using my left endpoints, I'm going to take my delta x of 2 times my function value at 0, plus my function value at my next left endpoint, which is f of 2, plus my function value at my last endpoint of f of 4. Looking at the table, I know that f of 0 is equal to negative 6, f of 2 is 8, and f of 4 is 30. Taking negative 6 plus 8 plus 30, and timesing that by 2, we end up that our left-Riemann sum approximation of 3 subintervals for this table of data is 64. You do the right-Riemann sum. So R3 is going to be equal to our delta x, which is still 2, but this time we're going to times it by our right endpoints, which would be f of 2 plus f of 4 plus f of 6. Please show this as part of your work. And then we can substitute in our value. F of 2 is 8, f of 4 is 30, and f of 6 is 80. Adding those together and dividing by 3, we end up with our right-Riemann sum to be equal to 236. Okay, next, I want you to approximate the using your midpoint Riemann sum with 3 subintervals. So M3 is going to be equal to our delta x, which is still 2, times our function value at our midpoint. So our midpoints is halfway in between these. So since these are nice equally spaced, our first midpoint is going to be f of 1. Our second midpoint is f of 3, and our third midpoint is f of 5. Using our table, we figure out that f of 1 is equal to 0, f of 3 is equal to 18, and f of 5 is equal to 50. Adding those together and dividing by 2, multiplying by 2, I end up with that my midpoint approximation for the area under this curve is 136. Last but not least, use your trapezoidal method to approximate the area. And with the trapezoidal method, you take delta x divided by 2, so in this case that's 2 divided by 2, or 1, and then I take f of 0 plus 2 times f of 2 plus 2 times f of 4 plus f of 6. So trapezoidal T3 is equal to 1 times f of 0 is negative 6, f of 2 is 8, f of 4 is 30, and f of 6 is 80. Multiplying those, adding it, and multiplying by 1, I end up with my trapezoidal method approximation of area is 150. Now that we know how to approximate area with these 3 methods, next thing we're going to look at is how to define the area of a region of the curve, find the exact area. Now the condition that needs to be met to do this is that the function must be continuous and non-negative on that interval from A to B that we're looking at. And the area of the region bounded by the graph of the function at the x-axis and the vertical lines x equals A and x equals B is found by the following formula. Area is equal to, now what we're going to do here is we're going to take the limit as n goes to infinity. So we're going to draw infinitely many thin rectangles that we can draw in this interval from A to B. And when we draw these infinitely skinny, infinitely many rectangles, we end up finding the exact area under the curve from A to B, the x-axis, and our function value. So this pink highlighted area here is the area that this formula will find. So now it's no longer approximation, we're finding the exact area under the curve. Okay, so we're going to use the same sort of like formulas that we used in our approximation, but this time the difference is instead of having n equals 2 or n equals 3 or n equals 10, we're going to make n go toward infinity. So we're going to use some limits to infinity. So area is equal to the limit as n approaches infinity of the summation, so the sum of all the terms, sum of all the areas of the rectangles, of I equals 1 to f of the height of the first rectangle, which we'll call f of C1, times our width of our rectangles, delta x. And so where x of I plus 1 is less than or equal to C1, which is less than or equal to x of 1. So it's in between that A and B. So each of those endpoints, CIs, are in between A and B. And our delta x is still found by taking b minus a divided by 2. All right, let's see how this actually works in a problem. So we're going to find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, x equals 0, and x equals 1. So I'm going to start by plugging into our formula the limit as n goes to infinity of the summation of I equals 1 to n of f of ci when this times delta x. And so now we need to figure out what c sub I is equal to and what delta x is equal to. Okay. We assume in this formula that c sub I is equal to the right endpoint of each of these infinitely small rectangles that we're forming. And so therefore c sub I will be equal to I divided by n. And our delta x is still found by taking b minus a divided by n. So in this case, b is 1, a is 0, and n is n. So we get 1 over n for our delta x. Okay, now we're going to replace that I sub n into our function. So we're going to find f of I sub n. So placing I sub n in place of every x in our function, we end up with I sub n quantity cubed times 1 over n. And then the limit as n goes to infinity of the summation of I equals 1 to n. And we're going to distribute that cube. And then, and now we're going to multiply our n's together to get n over the n to the fourth. So I cubed over n to the fourth. Now n is considered a constant. It's a number because remember our upper and lower bounds need to be constants. So I can factor that 1 over n to the fourth out. So I have the limit as n goes to infinity of 1 over 4 to the n power of I sub n, I sub 1 to n of I cubed. And now I can use our formula, our summation formula for I cubed that we learned at the beginning of this section. And replace that summation with n squared times n plus 1 quantity squared all over 4. And now it's just algebra. So I'm going to simplify inside that limit. First I'm going to figure out what, I notice that n to the fourth and n squared can simplify down, and I can cancel out 2 n's on top and leave it with n squared on bottom. And I can bring that 1/4 out and just put all the n's together in a fraction. Okay, simplifying that down, I end up with 1/4 times, and I can bring a constant out of the limit, so I can bring the 1/4 out of the limit. Simplifying that, I end up with n plus 1 times n plus 1 over n squared. And so 1/4 the limit as n goes to infinity. Well, let's figure out what n plus 1 times n plus 1 is using our full method. We get n squared plus 2n plus 1 all over 2n. Now I need to get rid of that fraction by splitting up our fraction, our common denominator, and I can rewrite it as following. Simplifying each of those individual terms, I end up the limit as n goes to infinity of 1 plus 2 over n plus 1 over n squared. Now I can evaluate my limits to infinity. So I know the limit as n goes to infinity of 1 is just 1. And the limit as n goes to infinity of 2 over n is 0. And the limit as n goes to infinity of 1 over n squared is also 0. So my exact area under this curve is simply 1/4.